What do you guys think about this one?
I don't like it.
Okay, that's because you spent a month in another country.
It looks kind of scary.
It's not so bad. So remember, I said all we're gonna need here is the natural log formula. So let's look at the formula that we would use if if we knew it, but we're gonna pretend like we don't know this. But first, the derivative with respect to x of a log base a of u is equal to what?
1 over u natural log of a times du dx.
All right, so that's the formula we would use. And in this case, then, u would be the square root of x, and we would plug that in here, and the derivative of the square root of x here, and we would get our answer. And obviously, the a would be 5. Let's pretend, though, like we forgot this formula. We don't know it. What we're going to use is the change of base formula for logarithms. You guys remember the change of base formula?
No.
Okay, so here it is. The log of b with base a is going to equal what?
The curly.
Nope,
So
not
Miss
that.
Wallace called it.
No, it's not the curly.
Oh.
Sorry.
Getting old.
It's the log of b to any base over the log of a to that same base. So we can introduce a totally new base, a completely new base to our logarithm, and we just divide those logs. You guys remember this?
Yeah.
This look familiar? All right, which base do you think we're going to use here? Instead of c, we'll use e. Because if we use e as our base, then it's what kind of log? It's a natural log. And we know how to take the derivative of the natural log. That's the one that I said you absolutely need to know. So what we're going to do here is we're going to change this equation using that rule. And that's going to make this the natural log of the square root of x over the natural log of 5. Again, the natural log of 5 is a constant. So I'm going to rewrite this in a way that kind of reminds me of that. This, the natural log of 5, or I'm sorry, 1 over the natural log of 5, I'm going to pull out front and multiply that by the natural log of x. Okay, so this is just some number. Some number times the natural log of the square root of x. Okay? Does everybody see why this equation right here is the same as this? Okay, now, the derivative of that, I'm going to use y prime here. Y prime is the derivative of y, or we could write dy dx, is going to equal 1 over the natural log of 5 times the derivative of the square root of x. I'm sorry, derivative of the natural log of the square root of x. What's the derivative of the natural log function? 1 over u times du dx. So in this case, 1 over the square root of x. And then the chain rule says we have to multiply by the baby. The baby function is the square root of x here. And what's the derivative of the square root of x? Well, the square root of x is x to the 1/2, right?
X to the negative 1/2 over 2.
So the derivative of that is going to be 1/2, x to the negative 1/2. That's the power rule. You guys remember the power rule?
Yeah.
Okay, so we multiply the exponent out front and then subtract the 1 from the exponent. So that's the same thing. If we want to keep it in radical form, that's the same thing as 1 over 2 square root of x. So the derivative of square root of x is 1 over 2 square root of x. So we have to multiply this then by what? 1 over 2 square root of x. Are we done? No, we should probably simplify that, right?
Yeah.
Don't you think?
Probably.
Yeah?
So what exactly is the chain rule? You said that earlier, but
We'll get to that in a second. I'll help you out with it. Okay, what should we do here?
Multiply square root of x's.
Okay, multiply the square root of x's. And what do we get?
I don't know.
Uh-oh. There it is.
I can tell you.
What do we get? So we have 1 over a bunch of stuff.
2x only 5.
Okay, 2x times the natural log of 5. Is that the same thing we would have gotten if we had used the formula, this formula up here? Did anybody try it? Okay, let me ask this. And when we're dealing with natural logs and exponential functions, we might end up with some restrictions on the domain. With the log function or the natural log function, what kinds of numbers can we take a logarithm of? Positive? Can we take a logarithm of 0? No. We can't take a logarithm of 0 because I'm going to just do the natural log here to keep it simple. If the natural log of some number, I'll call it z, the natural log of z equals 0, then what that means is e to the 0 equals, I'm sorry, I did this backwards. That's not what I wanted to do. If I want the natural log of 0 equals z, then that means that e to the z equals 0. Well, what do you raise e to get 0? Nothing. Now the limit as z approaches negative infinity is 0. So when z becomes a really, really, really big negative number, it's going to get really, really close to 0, but it's never going to equal 0. So we cannot take the natural log of 0. Can we take the natural log of any negative number? Say negative 1. Can we raise e to some power to get negative 1?
No.
Well, think about it. E to a positive number is going to be a number that's bigger than e, right? So it's got to be positive. What about e to a negative? Say e to the negative 2. What does that mean? 1 over e squared. Is that positive or negative? Positive. So no matter what, e to any power is always going to be positive. So we cannot get a negative. So that means we cannot take the natural log of 0 and we cannot take the natural log of a negative. Or that applies really to any logarithm. So we know this can't be negative. We also know it's not negative because we're taking a square root. So we do have a domain restriction here. X has to be bigger than what? 0. Which means that when we take the derivative, it really doesn't have any meaning if x is less than 0. We could put a negative number in here and get an answer, but it doesn't have any meaning because the graph of this is never to the left of the y-axis. The x's are never going to be negative. So we would want to say here that x is going to be greater than 0. Does that make sense? Because to the left of 0, the derivative doesn't make sense. It doesn't tell us anything about the function itself. Evan.